Like I say, we've got all the soluble loaders going forward, including all the nutrients. That flow is now recombined and now comes through to, this is the secondary or biological treatment process. And I'm sure you can all tell me that what you can see is an activated sludge plant. So what we have is actually, we have 6 process lines, all 6 parallel lines, all identical, 6 lanes. There are 4 in this block. There's actually 2 in the next block down, but they're all exactly the same in terms of volume. And effectively what we have is a long, narrow, relatively narrow channel, an activated sludge lane, but instead of building them long and narrow, you can build them in a smaller box, and the flow actually goes up to the end, comes back, and then up to the end again. So it starts at this end, flows up to the end of the first pass, back down again, and then back up. So very simple from a civil engineering point of view. You don't want to build big long oblong boxes that are 20 times wider, longer than they are wide. Effectively you build a rectangle and put 2 baffles inside it so the flow does that.
That's right.
It's fairly simple, yeah. So what we see here, although we've got 6, there are 6 what you call aeration lanes. Each one of those aeration lanes has 3 passes. So if you look at it here, you could say there was 18 lanes, but actually there's only 6. It's 6 tanks. So each lane has 3 passes. Mark is going to talk to you about biological nutrient removal next week in a bit more detail, but biological nutrient removal is a certain configuration of the activated sludge process that gives us, what we're after here is actually phosphorus removal. When we talk about nutrients in wastewater, nearly always we're talking about nitrogen and phosphorus. So up until fairly recently, certainly in the UK and most of Europe, the main aim of sewage treatment was to remove BOD and to remove ammonia, because both of those have an oxygen demand in the watercourse, and ammonia is toxic to fish. To upgrade further beyond ammonia, or BOD and ammonia removal, we then start looking on some sites at nutrient removal, where we start having to remove either phosphorus or nitrogen, or in some cases both. On our sites at the moment, all of our big sites have discharge consents and requirements for us to remove phosphorus. We don't yet have any to remove nitrogen as well, although certainly those will be coming. And in Europe, or certainly mainland Europe, quite a lot of the big sites also have nitrogen removal as well. So the way we will enable that on an activated sludge configuration is that the inlets to each of these lanes we can see on our left here, where they're not aerated. You can see that the lanes where we're not adding air, we've got the static surface with scum on the top we walk through. Those are anaerobic and anoxic zones. Yeah, so if we think of this whole lane as a single long tank, about 25% of that is not aerated, it's anaerobic or anoxic, and about 75% is, we can see here, aerated. So the flow is coming in, the settled sewage flow comes in, it's split into 6. A sixth of the flow comes through the head of this lane. It's mixed with the activated sludge from the end of the process, which is taken out the clarifiers and recycled back. So we've now got this mixed liquid, we've got the biomass, which is the activated sludge, that's all the bacteria we need to do the treatment. We're adding settled sewage to it. The first thing it sees here is the anaerobic zone. So the anaerobic zone has got no dissolved oxygen in it at all, and the biology now has to respire, or try and respire, and survive in anaerobic conditions. It can do that, it's got a very clever adaptation where it's able to do that. I won't go into details about it, but that enables the first part of the phosphorus removal process. So the anaerobic zone is there to select bacteria which quite like or can survive in anaerobic conditions, and those bacteria, one of the key functions of those bacteria is that they're able to remove phosphorus from the wastewater. The second part of the unaerated zone, it's also has no dissolved oxygen, but we call it an anoxic zone, not an anaerobic zone. Now the reason for that is that you won't be able to see from here, but below the water surface there is a certain amount of recycle from the end of the process into the head of the anoxic zone, which is the second of these unaerated zones. In the course of wastewater treatment, aerobic treatment through the process, we convert ammonia. We don't remove nitrogen, but we convert ammonia to nitrate. It gets biologically oxidized from NH4 plus to NO3. by returning some of the flow from the end of the lane to the anoxic zone, we've now got a zone where we've got no dissolved oxygen, but we've now got nitrate. We've got oxygen in the form of nitrate, or an oxidizing source in the form of nitrate. So some of the same bacteria and some different types as well will now actually utilize the nitrate as an oxygen source. So they will reduce the nitrate to nitrogen gas, and the nitrogen gases will just be liberated from the process. So the first part of the anaerated zone, the anaerobic zone, is designed to stimulate phosphorus removal. The second part of the anaerated zone, which is the anoxic zone, is designed to stimulate nitrogen removal. Yeah.
How do you reduce nitrate to nitrogen?
Okay, so it's what the it's the bacteria which remove BOD. So bacteria, heterotrophic bacteria, they're the ones that feed on organic carbon. Yeah, they break down big long chain organic carbon molecules. They get their energy by consuming them, the same way that we break down sugars and things like that and convert them to energy. Now that's fine, but and ordinarily they will do that aerobically. They'll use oxygen exactly the same as we do. We burn calories, we breathe air, we use oxygen to burn, to break down the organics, release the energy. Ordinarily they would do that. In an anoxic zone, they haven't got oxygen available, so instead of oxygen they will now raid the nitrate and reduce the nitrate to nitrogen gas and take the oxygen from use that as the oxidizing source. Yeah.
Thank you.
They're very clever. And actually I was saying the anaerobic zone, some of the same bugs also have a third trick. So they would always prefer to respire aerobically. If there's dissolved oxygen, they'll always use that first. If there isn't dissolved oxygen, they can use nitrate. And some of them are really clever. If there's no nitrate, they can actually start using, they can respire using phosphorus and do it that way. So yeah, some of them get quite clever. Sorry? A lot. Yeah. So without putting numbers onto it, the biggest single running cost by a long way of any actual research plant is oxygen transfer. So that big building behind you, yeah, the building we walk past is the blower house. So once we get past the anaerobic and anoxic zones, we're into aerobic treatment. To meet the oxygen demands for aerobic treatment, we need to supply air, and we can see on the surface now that there's air being introduced at the bottom of the tank. So there are rows and rows of air diffusers, but that air has to be compressed because the water depth here is about 5 meters. So we're now having to blow air into the bottom of the tank 5 meters deep. And that building there is where the compressors are to supply the air. It's only at low pressure. The compressors supply air at about 800 millibars or 700 millibars or something in that order. So that's where probably 60 or 70% of all the operating costs of the whole site is electricity consumption for aeration. And so that activated sludge is very good in that it's very compact, it gives us good treatment, but it's relatively energy intensive. You require quite a lot of oxygen. I can't tell you off the top of my head what the air power consumption is here. There's probably something in the order of about 700 or 800 kilowatts of power being used in the blower house to produce this air. And I'm saying it's a big, from a carbon footprint point of view, it's one of the biggest. It's one of the biggest consumers because it uses electricity. From a commercial point of view, a financial point of view, obviously, it's one of the biggest costs, biggest aspects of operational cost. And that is one of the downsides of the activated sludge process. It's very good. It's very compact. We can design it well, treat very good standard effluents, but we're always looking at ways of reducing the energy consumption.
So the most energy consumption bit is the aeration part?
Yep. But by a long way, yeah. So if you look at lower technology forms of treatment, trickling filters, or even going all the way down to pond systems, you can design those to produce very high quality effluents as well. You can actually get any quality you want, but you need a lot more space, a lot more land, but you don't need the power. So it's a trade-off. We'll walk through the process a little bit.